Okay, I guess we can start. So hello everyone, welcome to the ITC Colloquium today. So today we will have the speaker, Professor Brenda Frye from University of Arizona. She will be, she has been in University of Arizona for more than 10 years. She taught the graduate course of galaxy cluster. So all my knowledge of galaxy cluster are actually from Brenda, and she is an expert on this, on cluster itself, on gravitational lensing, and also the broad galaxy evolution in general. And over the past few years, Brenda's research is mostly focused on JWST observations from the guaranteed time observation called pearls, and which she will be talking about a lot of that today. I think Brenda will take it away and talk about one of the greatest discoveries JWST have been made over the past few years, at least in my mind. Thank you.
Okay, thank you all. Hope everyone can hear. So the measurement of the current rate of expansion of the universe, h0, today differs from the measurement made at the time of the CMB, and then extrapolated 14 billion years using lambda CDM. This is referred to as the Hubble tension. It persists, it puzzles us, and has become one of the interesting problems in cosmology. So today I'll give a talk that addresses this tension by presenting a new value for h0 using lensed supernova. Okay, so the talk will consist of 3 parts. In the first one, we'll review a relatively non-standard method for finding massive gravitational lenses that maximizes the chance of explosive transients in the background. And then we'll move on to introduce a representative set of clusters observed by JWST, some of the first ones as a part of a GTO program, as Fengwu mentioned, called pearls. And then finally, we'll introduce this special supernova, that happened to have the right geometry, and the measurement of h0. Okay, so I show this introduction, which obviously isn't a galaxy cluster, because I had to go to the STSCI webpage a number of times since I work a lot with JWST, and was very lucky to find the cluster in which this supernova was discovered right on their homepage. So I found that to be a nice way to get us going. So I don't work alone. I have a large team of people, as we'll kind of introduce you to throughout the talk, including a great many young scientists who are highlighted here in yellow, graduate students and postdocs. And there's that cluster. Let's see if this works. Okay. So a long time ago, before the first stars and before the first galaxies, we say we had the dark ages. But the universe wasn't dark in terms of its activity. This was a time in which the dark matter was very rapidly assembling the infrastructure into which the baryons would later rule. Tiny variations in temperature led to tiny variations in density, which then grew. The parts that were denser grew because the gravity was slightly higher there. And these denser regions, over time, formed, in the standard lore, what we call the nodes of the cosmic web, and they were fed and linked by filaments. We think that these overdensities probably became excellent emitters of rest frame far infrared radiation by the time of cosmic noon, redshift 1 to 2 or so, as a result of dust reprocessing of light. That's the first topic. So how massive structures form inside of these overdensities releases energy into the universe. This is the extragalactic background light. Okay, the primary component of that light is the cosmic microwave background, and the second most important component is the cosmic infrared background. Cosmic infrared background, it consists of dust reprocessed light. So stars emit light, the dust absorbs the light, reprocesses it, and re-emits it in the far infrared rest frame. So if we look for the peaks in this light, we should find the peaks in the CIB, and those should correspond if we get this right, to the peaks in the mass, in the overdensities. Okay, but these types of sources would be really rare on the sky, and they would be detectable at redshift 2 in the observed frame submillimeter wavelengths, making Planck telescope relevant. Okay, so you might say people have used Planck to discover galaxy clusters before by the Sunyaev-Zeldovitch effect decrement, right? Very successful experiment, cosmological experiment, and that's different from what we'll talk about today. We set out to try to find clusters using the same data set in a new way, by color, the way astronomers do it. So we used Planck to try to find those sources that would be bright in the submillimeter and also red and compact, and so potentially at high redshift. These are the so-called Planck cold sources. Okay, so very well, what did we find? Well, we identified the brightest 2,000 such objects that fit our criteria using all available extragalactic sky and Planck, and published that a while ago. And then we followed up the brightest 10% at higher spatial resolution with the Herschel Space Observatory that could also observe those wavelengths. And what did we find? Okay, did we find overdensities? Well, we found two types of objects. The first type, which was the vast majority of sources, I just show one of these 200, unless we could come later and see some more, but one of these 200 here is representative of the vast majority. We found that when we observed at higher spatial resolution, that within this unresolved Planck beam, what appeared are circa 10 individual sources within each beam, each consistent with being dusty, star-forming, star-bursting galaxies, okay, in close projected proximity. And the sum of those 10 star-bursting galaxies was sufficient to push it over the flux limit, flux density limit, and be detected by Planck. These are our protocluster candidates. We're slowly going through these and asking the question, could these be the progenitors of modern-day massive galaxy clusters? It was the vast majority, and that's not what we're talking about today. Another talk, but we don't have enough time. We'll talk about the small minority of sources that were identified by this same method that instead remained unresolved even at higher spatial resolution with Herschel. These are objects that were singularly detected by Planck, galaxies at redshift 2, turns out detected by Planck because they are strongly lensed by a galaxy cluster lens that Planck does not see. Instead, it identifies this background source. And each of these sources shines with a flux density equivalent to a factor of 10 or more, so with the equivalent of 10 star-bursting galaxies. Okay. And it's these lens sources that are the subject of this talk. Here is just a quick photo album of those brightest 10%. You could see the vast majority are, well, you can't see much from your distance, but they're consistent with being protoclusters apart from some of these points at the top and points at the bottom. We did find 12 of these 228 sources that were consistent with being these strongly lensed sources, and at still higher resolution of Hubble Space Telescope, we see indeed that they break apart still further into many lensed sources. Okay, so once we have the lens sources, what can we do with them? Well, light from an object gets bent past an object in line of sight, which we call the lens, into some new position. And this might work. If the surface mass density is high enough, then you can get, say, another image in another position. And those images make some angle, theta, with the optic axis. And the whole time, the source is actually hidden at some other position, beta. And we can say that the source position beta is equal to this theta minus the deflection angle. That's the lens equation that we see up here. Okay, so I don't know, it may be pretty intuitive that for some kind of point mass, the kind of work I do a little bit with Rosanne Di Stefano here, CFA, that the deflection just goes with 1 over the impact parameter, beta. Okay. But for a distributed mass, then if you have a particular lens in mind and a source, then the deflection is a constant, which just depends on the velocity dispersion of the cluster itself. Okay. So while deflection can be, interestingly, a constant for objects well behind a cluster, the magnification is a strong function of position, with the maximum at the position of the Einstein ring. Here, we could show this obligatory plot of pushing a wine glass across an image of the HDF. Okay, and then I can also bring your attention to this image here, which is relevant if we just consider the plot we showed in the previous slide from the side, but now view it face on. We would see the optic axis here, the source position here, and now I've given the source some morphology. We've introduced a checkerboard, a white and a red checkerboard, and we can see that one image of the source, if it is strongly lensed, can appear here, just interior to the Einstein ring, boosted in size and brightness, and given some pattern. And if we get a second image, that image will cross the critical curve. And on each crossing of the critical curve, it will change in parity. So we see the parity change. So now I can ask you all a question. Can you see if we look at this image of galaxy cluster 0024? I won't make you guess the telephone book name, but can we, whoop, that really didn't work. Okay, can we find, okay, I need to, okay, good. Can we find an object here that would follow this type of morphology and parity flip? Anyone? Yeah, okay. What else? Anyone else? Yeah, okay. So let me go ahead and put down that image for you here. There we go. There's the equivalent tangential critical curve. I chose a cluster that does have a lot of circular symmetry, so it's not so complex. And you can see one image here. I suppose I could just point to it like this, where there's a kind of a compact nose, and you see a little circle, a couple of circles on either side of it. And then if you see another image of it, across the Einstein ring follows the same color. Surface brightness is conserved, and it's the same object. And here when we cross the critical curve, we see that that little nose now appears on the left, and the left, and the left, and those circles appear on the right. So we can just look at these objects, and you can already impress your friends, even if you're not a cluster lensing person, with this information. Okay. But galaxies like this don't really exist, right? We have a character from American folklore called Two-Face, right? But those don't exist, right? Let's keep this in mind. Okay. So when we have a gravitational lens, what can we do with it? Well, we do want to know how that mass is distributed throughout the cluster. The point of a lens model is to build the two-dimensional map of its mass, surface mass. We do that by obviously identifying the major galaxy sources, and then we can put down 2D profiles, in this case, Navarro, Frank, and White profiles. Next, we need to identify all of the other members of the lens. These are objects that are circled, are all obvious members of the lens itself in the intervening source. We do that searching by color or by the 1.6 micron bump if infrared information is available. And finally, of course, if we have, in this case, we see 3 images of the same object. We have an image system in which we have one galaxy whose image appears in multiple locations on the image plane. This is an image system or an image multiplicity. You'll hear it called something like that. In that case, we have extremely good constraints in what the lens model can be, because it must be able to have these 3 images that we observe and find a solution that traces back into one position. And then finally, we use all this information as inputs to to construct our lens model. Now we can get to the fun stuff. So over 60 years ago, it was proposed, a kind of classical idea for how one can measure H0. It was originally envisioned for multiple image supernovae, indeed. And it goes something like this. If we have, in this case, another example of a single galaxy whose image appears in false color in pink, A, B, and C appearances, then there'll be different path lengths from the source to the observer. Those path lengths mean that if there's a transient event, then there'll be a delay in the arrival time of the photons to each one. So if we imagine some kind of event in image A, then we can produce some light curve. Sometime later, we can get another event in image C, and we can measure this time delay. And then sometime later, there'll be also an image in B, and we can get another light curve. You get the idea. I don't need to make this plot too messy. But we measure this time delay. And that time delay obviously depends on the observed positions of the supernova. And so in that sense, it obviously depends very much on the lensing potential of the lens. And we can represent that by the Fermat potential just here. Now, the time delays also carry cosmological information in the form of ratios of angular diameter distances of the lens and source. And those appear in what's called the time delay distance. And that time delay distance goes inversely with H0. So in sum, if you have a stopwatch and you have a lens model and you know the lens and source redshifts, then you can measure H0. Sounds easy enough, but until now, it's only been done once before. They're pretty rare. You might be saying to yourself, though, I've heard of this, for years and years and years. And you have, because this approach has been used to very successfully measure H0 in the case of quasar lensing events. Okay. And this is really a labor of love. I've been involved with some of those projects as well. That it can take usually a minimum of 7 to 10 years of monitoring in order to measure those time delays, because the quasar variability, is not very predictable. The physics is not really well studied, and the image separations are extremely small, typically. So it's a difficult job. So we won't talk about that today either. But the first multiple image supernova was called Supernova Refsdal. You may have heard of it. It was a type 2 supernova, found at a redshift of 1.5. You can see a quick picture of it here, in which there was one supernova in which it was lensed into 4 different pieces, like an Einstein cross. And then a year later, there was another image here, and a time delay was measured, one time delay measured between those two. It caused a lot of excitement, and 23 different lens modeling teams produced their own lens models. And those values for H0, this is H0 as a function of magnification, everyone had their own value for H0, okay? So there was some frustration here. What was the problem? What was going on? And it was long understood, but shown fairly recently, one way to sort of break some of that degeneracy between the lens models, which is to say, a correlation was found between the value for H0 and the value of the absolute magnification of the image. Nice idea, but Supernova Refsdal was not a standard candle. Yeah?
So no time delay was measured for the inner deflector?
No. Yeah. Good question. Thank you. Yeah, that's right. Yeah. But be careful, because an astute observer would see that supernova just disappeared. So you have to act fast if you want to follow this up. Okay, so in sum, H0 measurements do test lambda CDM, and it's largely successful. It's beautifully successful, but at the same time, differences have emerged, usually exemplified by these experiments here with the smallest error bars, the SHOES program, and the CCDF program, HF, run by Adam Rees and Wendy Friedman, compared with the Planck measurements here. So the tension remains, and one can ask, is there room for more? Yes. Yes.
So this supernova Refsdal, you say it's not a standard candle, so it was not a 1A?
It's not a 1, it's type 2.
It's a type 2, that's the reason.
It's a type 2. Yeah, so any explosive transit will do, of course, for the time delay measurement. And that was a type 2. Okay, so let's move on to some data. Okay, so around about 10 years ago, even before that, I was searching madly for how to get more clusters observed by the JWST. And as you may know, that type of opportunity is typically feudal in the US, meaning you have to go to some local kingdom and sell your project. So I was very lucky that Roger Windhorst at ASU allocated some time from his larger GTO program for us to observe some galaxy clusters. So we pulled together a team from many places around the world, selected 7 different galaxy clusters that we would observe. And the idea was to study the dark matter in the cluster, study the objects behind them, and so on. So of these 7, we all got together and agreed that we would observe 4 that are household names. Anyone who has looked at a cluster before or read much about them will probably have heard of all of these. But then I really stuck my neck out and said I want us to observe also 3 clusters that would otherwise not get observed because the opportunity of GTO time is to be a little bit bold. So we also have 3 clusters that were selected by more non-standard techniques in order to shake the pear tree, maybe learn something about them. One of them was this one that I described, selected by the Planck-Herschel color method. That's G165 up here. And others were selected out of big data sets by group finding algorithms and on searches, generally speaking, for the largest critical curve on the sky. So we took several years to build up our teams, to train people. I started from training first-year undergraduate students so that they would be graduate students by the time they could participate and be fully trained up in their work. It was a great deal of fun. And then round about summer of 2022, we got our observing schedule and saw that our first cluster would be observed 3 weeks after first light of JWST first light. So we were ready. I felt like we were backstage. We had been practicing for years. We want to be very fast. It's a GTO program. Some of the data would be made public out of goodwill, and we wanted to engage the community and so on. So we were ready to all jump out on stage and do our jobs. When we were kind of sideswiped by interesting opportunity, which is that, I don't know if you remember, everyone must remember, President Joe Biden suddenly said, I want to do the PR for the JWST first light. And I'll do that on Tuesday night. And then the data will arrive for the astronomers on Wednesday morning. Okay, fine. So 40,000 degrees of sky doesn't really mean to necessarily be something that pertains to us, but I wouldn't miss it for the world, probably not you all either. We heard that there would be public data sets, and they were distributed, 4 different data sets, one of them on galaxy field something, didn't know. So we waited, we were delayed 45 minutes, bobbing our heads like a metronome to the elevator music, and then suddenly, you all remember this, right? Suddenly we get the PR, we see the galaxy field, and it's way in the distance. I don't know how this journalist could have been farther away. He's smashed up against the wall taking this picture. But of course, astronomers everywhere are madly taking screenshots and blowing it up and trying to see what it is. I don't know if you can see from there, but maybe you can see from here. It's a lensing cluster. Wow, this is exactly what we had trained for. Our little niche of astrophysics is this very type of activity. It was the dress rehearsal that we couldn't have asked for. It was a gift that fell out of the sky right into our hands. It arrived late on that Tuesday afternoon on the West Coast. So my student and I just started looking at it right away. On the East Coast, people were kind of starting to, close up for the night. Europe, a lot of other places, difficult timing. So it was our job for the team to start seeing what we could do. So we started identifying image systems here. This is my student writing them out. We worked quite late doing that and then sent it off to the team over Slack and email to see what would happen. I didn't require that our cluster team engage. We didn't require that till our first clusters came in, but to see what happened. And by the next morning, boy, were we surprised. We didn't have to ask for anything. Everyone else had chimed in. We didn't, obviously, I woke up pretty early to see what would happen. And in the end, our team discovered 18 image systems, actually like 14, I think 4 were known previously. We had been madly reading up on any literature. We hadn't heard of this cluster. No one had before. There wasn't a lot going on. But at the same time, we also had to have team members getting themselves used to the different JWST data sets, which were handed out. We also have an interesting case here of another giant arc. You can use your skills here, not that skill. And we identified an interesting case of a galaxy that's lensed into a giant arc, as you see here, with 2 what turn out to be star-forming knots, sort of different sizes and colors, that get parity flipped on crossing the critical curve. You can use that skill again. And on top of that, there's even little, and they'll cut out little blue ones you might see, little tiny blue dots. Those also are doubly imaged. But then there's a tiny red one here that is not appearing on the other side. We think might be the first discovery of a transient. So our team went bananas, and at some point on the second day, I said, maybe looks like this is writing up itself. And my student, Massimo Pasquale, ended up writing a paper which we submitted 3.5 days after the data were received. And it was one of the first 2 papers submitted worldwide using any JWST data. The first one was submitted to AppJ 12 seconds prior to ours. I have other stories that might be interesting. Truly, the only other part of the story I'll share is that I told my student, okay, you can have off until Monday. I don't know what they do. Probably come back on Monday, and you might hear from the editor or something. But no, 30 minutes after submission on a Saturday afternoon, the editor wrote back saying, not that they received our manuscript, no, but that it had successfully gone to referee. So they were also preparing in their own way for papers to be submitted early on.
How long did the referee take?
Well, there you go. Thank you. That I think I planted you in the audience. So no, it was a proper process. But the editor got back to me really quickly and said, "Do you want to make this a letter?" And I said, "No, because we worked so fast. A letter is a poem, as I see it. It's a poem. You have to fit the constraints. You have to fit the figures and tables. And so I said, unfortunately not. The constraints are limiting." And he said, "I'll waive all constraints." And I told my student, you'll never get this treatment again from a journal. So enjoy it now as a young graduate student. But yeah, then it went through the process, but there's obviously some ways to fast track it. I think there may have been some pride at the level of the journal also to try to get out papers early on. And that second paper was arrived 12 seconds earlier, was made to a different journal, actually. It was made to a different journal, it wasn't AppJ, yeah. So maybe there was some competition, I don't know. But anyway, thank you for the question. So then, I don't know if some of you know Mark Davis, but Mark Davis rung me up at that point and said, "Congratulations on riding the Webb wave." So we put our Pearls logo on top of a wave there. So our dress rehearsal worked. Couldn't have been more pleased once we recovered our sleep and so on. And then 3 weeks later, as promised, we then received our first data from our first galaxy cluster. This is a famous one called El Gordo, the fat one. It is a pretty high redshift massive cluster, as massive clusters go, nearly at redshift 1, and is interesting because it has such a high mass, around 10 to the 15 solar masses out to the virial radius, that some people say it might break lambda CDM cosmology. So with these new data and an incredibly beautifully detailed data set, we find that it doesn't break cosmology, so that's good. But anyway, so we had now a different type of problem. We had now an embarrassment of riches. Instead of a circa 10 or so image systems, here we had 51 cases of individual galaxies that are multiply imaged in the image plane. We had a large number of lensing constraints, as we call them. You can see them labeled here like an anatomical diagram, and a large number of cluster members. So we were able to really race forward again to identify. I'll just show you one of those 51. It's what we call ARC9. In this false color image, we see a checkerboard galaxy, part white, part orangey red, which flips in parity on each of its images as expected from lensing theory, and which tells you right away, just looking at that morphology, that the critical curve therefore has to be passing through something like this, as we see presented here. A few more papers came out all at the same time. Oh, right, this shows you that maybe two-phase lives. Okay. So we did a paper on some very detailed modeling of a near-Einstein ring. And we identified a lot of low surface brightness sources and detected what we think is a star at cosmological distances. So all of that was well and good and very exciting, but then it got better. So I think as I was explaining to David Charbonneau just here at coffee, when the data for another cluster arrived, this is the Planck-Herschel selected cluster. We all assembled on Zoom, assembled in the office. I remember going to this nearby Jasper room that Xiaohui Fan keeps and bringing in every chair from that room into my office, and they're standing there. And I thought, oh, we'll just do like a spaceship tour and so on. But literally within 1 minute of looking at it, we said, what are those 3 dots that weren't there before? Stuck out like a sore thumb. And I said, I know. It must be a satellite of the galaxy. You see that they can't be random interlopers. Why can't they be random interlopers? Because you can see that the pattern of the galaxy near it in this point source flips in parity twice. Be rather extremely coincidental if that was some random low redshift interloper. They're probably together. They're probably being lensed together. At the very least, they're in close projected proximity. But not only that, but it was bright, 24th magnitude. So that means that it was 3 magnitudes brighter than the limiting magnitude of a single orbit HST exposure. Extremely bright. We also had 3 points to go on a light curve. If this is really some transient, we'd have 3 points. And when we put those 3 points onto a light curve, it brought back and it estimated that we had a type 1a supernova to 95% probability. So, what would anyone do? We started typing madly, okay, and falling asleep at the same time. It took 6 days from that discovery to be able to submit our proposal for our disruptive JWST DDT follow-up observations. And I think I slept with the cell phone under my ear to hope that I could wake up quickly when some new news arrived. We did. As we were writing the proposal, we also obtained DD time from the LBT and measured the spectroscopic redshift of the host galaxy, which turns out to be 1.8, one of the highest redshift type 1a supernovae known. And only JWST can really be able to follow up this source in the infrared and get the spectra. We had a lot of young people working on this. I invited people as young as undergraduates onto all of my calls and planning calls. I had a very distinguished cosmologist who asked me, what good are undergraduates? And I said, well, at 3 o'clock in the morning when I'm working, guess who writes me and asks what they can do? And I needed people to go to the near-spec manual, go to this. It's a relatively new observatory. I had a lot of little tasks I could hand out. And I would say, go to sleep, do your problem sets. And they would say, we got 3 weeks ahead on all our problem sets so we could help out. So they have tireless energy, and it gave me energy. This proposal was accepted, executed, and it couldn't have been better. We ended up getting 3 epochs in total of 9 points for a light curve. Doesn't sound like a lot, but it turned out to be enough. And you can see the supernova is detected in, I didn't show all the photometry, but it's detected in every filter band pass, in every epoch. We caught the supernova quite close to peak brightness. We also obtained spectra. This is a spectrum of a type 1a supernova at redshift 1.8. Beautifully high signal to noise because of its really high magnification factor. And we also had a unique opportunity. We were going to set out to do a double-blinded experiment to measure H0 by this method of time delay cosmography. I had to set up 10 different teams to do it and hire a chief of blinding police who would be the enforcer, who would not be myself. We had 7 independent lens modeling teams. One group that would measure the time delays off of the light curves, another that would measure the time delay off of the spectroscopy, and a 10th one that would build the theoretical baseline, the H0 methodology. And then we had a team doing the observing and so on. Okay, so let me give a few highlights of the spectroscopy, and then we'll talk about just for a moment about the lens model, the time delays, and H0. Okay, so we had hoped that this would be one of those sources in which we would maximize the detection of explosive transients. We were actually quite lucky that we got it on the first try, I'll admit that, but we did try to select this cluster with that idea in mind. And by far the most common redshift of any object in the background is at the same redshift as the supernova, 1.8. The compact galaxy group at 1.8 of galaxies essentially that are bound, we think, to this host galaxy of the supernova. They have a source plane diameter of about 33 kiloparsecs, very tight group of 6 clusters with relative velocity of 900 kilometers per second. Okay, they're basically all star-bursting objects, and we found a second group at redshift 2.2. Okay, so we had the chance to just take, I would say, a lower limit on the star formation just by computing the instantaneous star formation rate off of the H-alpha line, then correcting for underlying stellar absorption, dust extinction, and slit losses. And when we did that just for these H-alpha sources, just these few that we could see on the near-spec multi-object spectrograph, we got values of hundreds of solar masses per year, which corresponded to about 1 core collapse supernova per year. And even that value turns out to be equivalent to the expectation from all 6 Hubble frontier fields combined. So if you do want to find explosive transients in the background of lenses, you don't necessarily run for the most popular clusters. You need to have some other criteria. Okay, this is our grand mosaic of the G165 galaxy cluster. You can say ooh and ah. Okay, it is really beautiful. Cluster members are obvious. Now we know, everyone in the audience, why, unlike other similar images that you've seen, why this one has giant arcs all over the image that are the same color. Why is that? Because they're largely at the same redshift. They have the same similar K corrections, okay? Nearly all these galaxies, vast majority, are at redshifts of 1.8 or 2.2. We're actually observing cluster lens by cluster. So we did have 7 teams. We got together for several weeks. We identified 165 cluster members and agreed upon them. We identified 21 separate image systems and all agreed upon them. And then we gave the same identical data to each lens modeling team. This is fairly rare opportunity to do that. We encourage them then to construct their lens models as they see fit without a lot of micromanagement, but with the expectation that they can't talk to each other at all about the results. Okay. And we also show this supernova here. This is the supernova Hope. We have an 8th team measuring the time delays. 3 epochs and 3 appearances means we have 9 points on the light curve. Here's one light curve. It does show this expected second peak in a type 1a supernova light curve at infrared wavelengths. We had the problem, though, that we lacked a template image, and we have a host galaxy nearby. So we did a very careful job of trying to subtract off that surface brightness before doing the photometry. Then we fed the photometry and a common set of light curve parameters for all the appearances simultaneously to an extended version of the well-known BSN models in order to get the phases and the time delays. So in short, we measured the 2 time delays successfully, and we also measured absolute magnifications. We did that for the first time because we have a standard candle, right? So we could compute the rest frame wideband photometry, and then compare that with a set of field supernovae to get the magnification. Here's a set of field supernovae. In addition to our other interesting facts, this is a very high redshift supernova. It also means that there were very few supernovas, about the third or so highest redshift type 1a supernova known at the time. Yes?
Sorry.
Not at all.
Light curve with the time delay.
Yeah.
So, I mean, I understand what you've observed, but then what you are applying a known template for what the light curve should look like? Is that how you are then deciding what's the time delay?
Yeah, we're applying a type 1a. Yes, a type 1a.
Okay,
Yep.
so you already know what to expect
Yes.
from a type 1a
Yeah.
at redshift 1.8 with an unknown magnification.
Yes. So we were able to pass on the information as a type 1a, which you could see this is a requisite, this is a bump that the photometry people would only see for type 1a's. And we were able to pass on the spectroscopic redshift
Right, okay,
and the designation as a normal type 1a. This is actually a normal type 1a.
okay. Which would have a light curve in that gray band.
Yes.
So you
Yeah.
know that it has to be in the gray band, but you don't know what the time delay between the three images is. And that's being fitted, and then
Right.
you're saying this is what you get.
Right, that's
Great,
right.
thank you.
Yeah, being measured, yeah, fitted and then, yeah, that's right. And it becomes then a set of observables. In the end, we end up having observables O, which comprise of a set of 2 time delays and 3 values for the absolute magnification. Okay, we computed errors rather exhaustively as well, and I can talk about that statistical and systematic, including a wide range. Yeah.
If you're solving for both the magnification and the time delay, then you're taking the 3 red points could move both left and right and up and down? So how?
No, so the magnification was measured by doing synthetic photometry based on our model and extracting the wideband rest frame photometry, and then comparing that with those in field supernovae
Okay.
at that same redshift. But to do that, we put a whole all-known supernovae and fit a curve in a few different ways that can try to interpolate between those few points at high redshift, if that makes sense.
So that's the standard, you're applying the standard candle constraint.
Yeah, that's right. Yeah, thank you. Yeah, perfect. Okay, but that's not all. We have spectroscopy, and in a kind of industry first, we're able, not to have to worry as these dear, very hardworking, really close friends of mine who study quasars, who take 10 years that's required to measure the time delay. We found a second way to measure these set of observables in a 3-hour observing block. And this is by obtaining spectroscopy of all of these supernova appearances at the same time. So normal type 1a supernovae are pretty well studied, or at least people who study them think they're pretty well studied. and so we're able to fit templates to these spectra in order to measure the phases and in that way get the time delays, and also to do the photometry in the wideband in a similar way and measure the absolute magnifications. So this was done also by a purely spectroscopic method that is not completely, but mostly independent of the photometric one. And the 2 groups didn't talk to each other. We have a very strong chief of blinding police, I must say. So I'll tell you later who that was. Yeah. Okay, so good, yeah. All right. Okay, if we get all that, then I said this is double-blinded, so we really set a day of unblinding, an event of unblinding. It was, a meeting that included everybody. This was the day that all of the time delays that were measured and all the lens modeling information had to be sent to my student, and he had to have his code written as well. And in real time, he would tell us what each knot is. And the chief of blinding police required that whatever value that was, it had to be in his paper on each knot, even if it was minus 900 or something. I mean, it would be that because there can be mistakes or something, right? So there's a lot of pressure, and my student Massimo is an extremely clever and pretty cool guy, but at the beginning of that Zoom meeting, I saw him shaking a little. So I took a few minutes just to review where we were, and then he came back and did really well.
Graham,
And
see
this
what
is what
Maxwell has
happened.
to tell us.
Okay, yeah, I guess I'll share my screen and share the plot. Skews high, large errors.
Wow.
This is the
It
weighted
mostly says
model.
woohoo. I'll ask you later. But anyway, I can show more of this later, but this is just to demonstrate to you that it really was, an actual unblinding event. When we saw this value for the first time, that value that you saw did change with respect to its final value because 7 mistakes were made, and those mistakes or errors are defined as problems that have objective solutions, and that then were approved by formal ruling from our chief of blinding police. Okay, so you can't say, oh, I know a way to improve my model. Oh, I just read a new paper that helps me. Those were not valid excuses. You had to show that maybe a coefficient really didn't get passed down to the next line or whatever. And all of those 7 errors then had to also be included in the paper. So what did my student do? Well, what we did is we gave a common just a fiducial cosmology to each lensing team. And then they predicted a value, say, at first for the time delays. We'll just talk about the time delays first. They were what was available for Supernova Refstal as well. And then that value for the time delay then would be compared with the measured values for the time delays, and H naught would be then rescaled. That would be how we would get our value for H naught. So we took a Bayesian approach to ask what is the probability of this H naught and a model given this set of observables. Okay, and it enforced 2 priors, really. The first was that each lens model would prefer a value for H naught such that the predicted values for the observables matched the measured ones. And the second prior was that those lens models that had predicted values that matched the measured ones would receive the highest weighting in the sum and thus have the most influence in the inference, H naught inference. Okay? So then we went ahead. I can show you the first results here in which we show the results of the 7 lens models, and the normalization that you see here reflects their relative weighting in the H naught sum. So first thing you might see is that just like for Supernova Refstal, H naught's values are all over the place, right? What a mess, okay? I'm still really proud of these guys, but all over the place. But we haven't yet played our next card, which is that we have a standard candle. And remember, there's a correlation between H naught and absolute magnification. If we then decide to include absolute magnifications into our set of observables, then we get a different answer. You start to see that some models start to be weighted more highly than others and get far more preference, and others are kind of losing out. And the errors went higher. But then we found when we included all of our information, which included the mostly independent spectroscopic time delay and the photometrically derived time delay, we obtain our final best answer. It does happen to favor one particular model. That's how the cards landed. And this is our final value for H naught. I should point out that from the time of discovery to the time of submission was 1 year, one of the shorter time scales, I think, for measuring H naught. So in review, we have our nice sort of plot of all the different values for H naught. We have the value from Supernova Refstal. We have now new ones to add from Supernova Hope, as we call it. There's our best value here, pointed right there. And my talk as of a month ago would have ended there, but we're very fortunate to have now the 3rd multi-image supernova discovered, and the 2nd one to be a standard candle. That one is still in the peer-reviewed process, but is obviously going to fly through very quickly. And that one is called Supernova Encore. Okay. Supernova Encore for a very good reason. One is that one time delay was able to be measured, and there's yet another time delay expected in a handful of years. Okay, so let's see. We're making a difference. So I can just sum up here and say this supernova hope gave us this value for H naught in a single step, avoids the cosmological distance ladder using this by this method, time delay cosmography. And it had this very interesting idea of being able to be double blinded, okay? And we were lucky also to have the standard candle so that we could assign grades to the lens modeling teams in a very rare opportunity, okay, to test how well their predicted values matched the measured ones. But I should say that these are pretty early days. We just recently obtained the first template image, which should improve photometry considerably. And that plus the new lensing constraints are likely to get us a factor of a bit more than 2 down in our uncertainties in the next year. Okay. We also are very interested to ask how the spectra itself, how we can learn something from the physics of the spectra and learn from our other ancillary data, such as the X-ray map, which shows this to be a mini bullet cluster, and some of the radio properties here, which can possibly constrain some of the intra-cluster medium properties in order to further lower or reduce some of those uncertainties. And so I might ask you, might this be a route to help us with the Hubble tension or just, a novelty? That's all. Yes, Ramesh.
I don't want to monopolize. Yeah, but I will ask my question. Yeah. Okay. This is beautiful. Obviously, this is the perfect object and and the data set. But then I'm trying to figure out in my head what goes into the final result. You are trying to extract a time delay between the different images. You're also measuring the magnification, for which you know the true original luminosity of a supernova. And these things all have to deal with, firstly, the Phillips relation, which will finally tell you what's the true luminosity of the object. And in the lensing game, there is this weird mass sheet degeneracy that people talk about.
Okay.
That is a worrying thing, but maybe when you know the magnification, it doesn't matter. I can't figure this out in my head. So I was just wondering whether you could explain how these degeneracies enter, and is that all in that error estimate that you give, etc. Yeah.
Well, thank you. I'll open by saying Ramesh is just being humble. I learned all I know from cluster lensing from Ramesh's review on the topic. Okay, No. So what Ramesh is referring to is mass sheet degeneracy is that, if one can imagine just putting down a uniform sheet of mass, say in the lens plane, then there can be isotropic magnifications that would go unnoticed, introduce a degeneracy to the models. This plagues quasar fields especially much. But it turns out that is not a problem in general for cluster lensing, even without the standard candle. That's primarily because it was shown that if there can be 2 or more image systems at different redshifts, then you can solve for that degeneracy. And in this case, we have it was demonstrated directly not to be a problem for supernova F-style in that case, and not for ours. But that's a really good question. And we did spend quite a lot of time in our paper addressing that, because it can be a concern since people are more familiar with these quasar scales in which we don't have that ability. And of course, the absolute magnification helps too. Yeah.
Relation.
Yeah. Well,
Will there be multiple solutions?
I don't know. We aren't able to make a lot of headway with just the one source. I think on that particular one. We do now have 3 cases of lens supernovae, and we can start to build a case. It's a very good question, too. Yeah. Yes?
So echoing that was amazing, all the data, the science. Okay, so in the era of Rubin and upcoming radio surveys, we're going to have a lot more time delay cosmography of explosive transient. So can you talk about the trade-off between galaxy scale deflectors to group scale deflectors to clusters? I mean, you just said in the low mass end, you don't usually get to break the mass sheet degeneracy, but I
don't know the nature of that. Do you mean in terms of detection of objects or
Well, I assume some of these clusters are it's harder to model their mass profiles versus a kind of NFW elliptical galaxy in the field or something. And you'll have more of them, I think.
I suppose so. It's not hard to get an initial model out for any galaxy cluster these days. We can certainly do it. Yeah, you could do that quite readily now with enough information to identify the foreground from the background and so on. And obviously, it depends on your question. The more constraints you have, the better it gets. And right now, we're a bit limited and we're getting more constraints for a particular case. But to get out, but to start that process, modeling clusters has become really relatively straightforward, at least to the point to make a discovery. And then those lensing constraints can come over time at no expense to the actual follow-up observations of the object. Okay.
So if you have like 500 strongly lensed supernovae from Rubin, you would focus on the clusters.
Well, I would. That's kind of my field. But also I would worry about the lower spatial resolution of a ground-based telescope compared to space, right? So I'm a little bit concerned about trying to focus your discovery on objects for which the image separations are 1 arcsecond or less. It's just a tougher game. It's possible, but more of a challenge. But even that level could be hard to follow up. Or when you think about the galaxy scale lenses, they're also very bright, right? So there's a considerable amount of galaxy light in the halo that contributes noise to the background sources, and those sources are very, very small in resolution. And then those sources that are noisy for other reasons too, and could have extended issues with other sources of noise. And they could have a lot of millilensing, microlensing effects as well, right? We're sampling the outer halos of massive elliptical galaxies. So there are some advantages to the clusters. We're much more separated. We have also the ability to be more separated also from the actual cluster members, so that there can be less contributions from those really devious sort of millilensing and microlensing effects as well, depending on the case. That helps, yeah. But we should search at all levels. I should add, for those who are interested, please talk to me after, that the galaxy scale lenses do receive 90% of the attention. Looking forward to Rubin, so if you want to join me to help search multiplying clusters, let me know.
Would you like to comment on your last question on your slide there? Novelty or great things to come?
Yeah, well, it depends on what you think. I mean, if I didn't get the point across, I believe in what I do. Okay, but the trick is to see what you all think as well. So there are sort of two routes to go here to kind of test how well we can do with this method. I mean, anybody can measure H0 to 10% these days, so ours is a bit below that, but 8.5% or so. So, I have friends, only friends now, and no enemies, because I agree with everybody. But so the idea is, these are early days. That was based on 1 year's worth of data. In the next year, we can really drop those uncertainties down and see where we fall. Our value for H0 right now is consistent with everybody, but leans a little bit higher, a little bit more towards the shoes result. I don't know what that will mean in the future, if it will come down or stay the same or go up. So that's one direction. The other direction is that, of course, now we have 3 ultimate supernova, and 2 of them came within a year and a half of each other, Supernova Hope, Supernova Encore. So I'm hoping once we can get 10 together, or even a few less than that, that we can start to combine this information and get a kind of...
And when do you expect to have 10?
Well...
10 years or 1 more year?
Well, it should be less. I mean, we found 2 in a year and a half, and there's a lot more attention paid to the problem now, at least in terms of the cadence with which clusters are observed by JWST. I think it will help. But so 10, good question. Probably, I mean, we could be getting some good candidates from Rubin once we get more happening here. But I would say between 5 and 10 years. I mean, I thought about this as well when I was giving a summer school talk, and I was thinking, when can we say that we'll solve the Hubble tension in general? And I found it was very hard to be honest about that. So I won't try to give too many numbers about the bigger question as to whether we actually have some interesting cracks in lambda CDM or not. But ultimately, that's what we hope to find out.
Okay, one last question. I apologize for the slightly wonkier questions, but
No.
so one is just a question on how the teams do the modeling. Was there a requirement that they all kind of like model down to the noise, or what was the kind of like level of residuals that the team kind of like allowed?
We were lucky. We did not require that. We were lucky to be able to not have to micromanage the modeling teams because their models would be graded. We would grade their homework by how well their predicted values for these 5 observables matched the measured ones. So we were able to allow a team. The requirement was that the team had to produce the results by the day of unblinding. Nothing can happen after that. A team that fell short just unfortunately didn't make it for this particular discovery and make the next one. But other than that, they had to work with the identical inputs, not only the 165 cluster members and the 21 image families, but we also gave them full photometry catalogs so they could also, and spectroscopy catalogs so they could understand to the best of everyone's knowledge where the foreground objects were, if their models took them into account, line of sight structure, or anything else. And we didn't have to micromanage that. If they did poorly, then their answer would receive minimal weight in the final H0 difference.
And then back to kind of Ramesh's Massey degeneracy style question. So you mentioned, of course, that having multiple source planes lets you break that Massey degeneracy.
That's
but
right.
what about, is there a systematic at all into whether or not you have multiple lens planes therefore, or any of the, is Supernova Hope actually potentially being lensed by an additional plane in between?
Yeah, that's a good point. I mean, you never know when there could be some devious mass placed somewhere, some cosmic conspiracy that you don't see. And we don't know a whole lot. But from all that we can gather, right, we gave any information that we have about line of sight structures to everyone. I can just say we have not found significant structures between us and the lens. And
No, I'm talking about, so between the lens and, say, the source plane at which Supernova Hope is at, are there any other galaxies at a redshift in between your primary lensing cluster and the source?
yeah, there are galaxies around, and I can show you a figure from Pascal et al. Plus 2025 where maybe it was in paper 2024 in which we show the redshift histogram. There aren't a lot of galaxies between 0.35 and 1.8. But there are a few, yeah, sure. Not massive ones, but yeah, we do obviously want to get the best answers, so we have done that study, and it looks pretty good so far, in that we don't seem to find a lot of line of sight structure between the lens and the supernova.
So let's thank Brenda again for the very nice talk, bring hope to us. So see you all in 30 minutes.